And I'm switching off.
Okay, thank you.
Thank you.
Sure. Okay, everyone, welcome back. Are you there? Are you still with me?
Yes, we are here, Professor.
Yes, we are.
Okay, good. So, okay, so you, I think you can still see my screen, correct?
Yes,
I hope so.
we can see.
Okay, then, okay, so this was the first approach. What was I saying? I was speaking about the different things. Okay, so this is on the screen now. I'm showing the straight line fit, the most simple thing that you can do. Even nowadays, even the mobile phone or a very simple calculator can do that. And actually, this is one typical case where you can do the calculations by hand, actually. But most cases we cannot do it. So let's move to our common interest in the relaxation data. Okay, so you can always get to this first page when you log in the system where you see your folders. I showed you a little bit of tutorial. Actually, I should have shown a little bit more just for reference. Okay, so we made this fit with a very basic fit with this straight line. You have in this menu, this drop-down menu, you have several examples. Some of them are named basic, others are named advanced, and others are named master. I think there are some cases here, maybe not in this example, in this menu here. Okay, it doesn't matter. So you can, as you wish, and is the best way to start, you can open any one of them by selecting one and then recovering it. And actually, are the same points as before. I changed the representation, and if I fit this example, you might find interesting to see that now is no longer a straight line being fitted. It's rather a second-degree polynomial. It's known as a parabola. And in colored, I mean, besides the black curve, you have the components. So the straight line, I mean, the horizontal, the constant A, the straight line goes through the origin. The origin now is at this point here. And also a parabola with a negative curvature. Therefore, it has a maximum. And all these three components together produce the black curve. So just for you to see, is as before, the function written in this way, this time as 3 parameters, and I'm using this backslash just to be able to create these additional lines with the line types and colors that help me to produce this nice plot. And you can do the same thing for all the other plots. Each one of them has a story behind, and you might find interesting to check in case you are interested. Anyway, so we can go now finally back and enter this tutorial NMR folder. Okay. The layout is the same, and you will have, as well as before, the 3 or 4 modes of that you can choose from. And here let's look at this example, which is MZ versus tau. I'm opening this one. And what do I have? I have this, it's called magnetization decay, but in this particular case, it should be magnetization recovery, or better said, in this particular case, is the inversion recovery. So this data was obtained in a conventional conventional NMR spectrometer, so probably a 300 megahertz machine. And so the magnetization was inverted and now is being recovered. And this is the type of evolution of the magnetization. And I can fit the data with this model. I did not show you the model yet. And this example that I'm showing here, someone asked about what would be if we would have not only one, but three components. And this is such a case. Here I draw, I'm showing you the example where we have three components, okay? So let me make larger. So you have, as before, as I've written already, and as you can see on the other window of my pad, you can see the magnetization M infinity, M0, M infinity, and exponential with the T1 is the same thing that you have here, with the exception of this here, which is actually a coefficient. Is a coefficient written in a rather funny way because it's the inverse of a sum of weights. And the first one, and you know, it's a relative proportion. Okay, it's the mixing factor, if you wish. And because I'm using this backslash as before, I'm able to generate these curves, and that is what you see here. So you see this time not only one component, but one. The violet, the green, and the blue are three components that are combined to produce this black curve. So you are fitting here. I was fitting a three exponential decay, and I was getting the respective values. Okay, and P12 and P13 are the weights. So they are obtained in a rather in this funny way as 1 over the sum. Okay, let's imagine that I want to calculate exactly what these factors are, okay? So one way, obvious, is to get these numbers, get the expression, and yeah, and make the calculation. So instead of doing that, I will just show you or use this opportunity to show another thing that you can do. You can use this calculator here. Please note that the fitting parameters gave these values and also give an estimation of the uncertainty of these values, of the parameters that were obtained. You have to use, or you should care, or you should take some care when you analyze both the value of the chi-square, of the q-square, or the sum of the squares, of the least squares, as it is called, and the uncertainty of the parameters. Depending on the program you use, this can be interpreted as such, like better said, this will be the uncertainty of this parameter, and this one will be the uncertainty of that, and so on and so forth. But you have to be careful when analyzing this, because in some cases, not only this chi-square does not have the meaning that you would expect, neither the uncertainty. Why is that? Because if you go back, if you notice, if you remember the expression I wrote about the q-square here, it is the sum, or it can be the sum, of the difference between the experimental point and the theoretical value divided by the uncertainty of the experimental point. So the value of the q-square depends on the uncertainty of your experimental point. So if you are not able to properly give the uncertainty of your experimental point the Q square that you get might be a very small number and have no meaning, no actually meaning. It might be the minimum, and being the minimum has a meaning because it will give you the best curve, or probably the best curve that you can get to fit your data, but the value itself, it has no meaning and cannot be easily compared with any other Q square obtained with any other function, because you are not giving the proper estimation of your uncertainty. This is one point. If you check here my data, I typed the value of tau. This is a magnetization as a function of tau for an NMR experiment. And I'm plotting here the magnetization, and here should be the uncertainty. And I'm using here, in this case, I'm using 1. And 1, in this expression here of my Q square, of my K square, sometimes I use chi square instead of Q square. A chi square is a statistical variable, and it has its own domain of use, and sometimes I exchange between the two. Anyway, if I use uncertainty 1 is a neutral element for this operation, so it's the same thing as not relying, not accounting for the uncertainty. So using 1 here means I'm not caring about the uncertainty, which means in the end that I cannot rely on this number. This number being very, very small does not mean necessarily that I'm a better fit, or this fit is better than another method which has a larger Q square, because the values are different or the uncertainty is different, okay? And this number here depends on the uncertainty I use. If you want to check that, I will change the uncertainty now to 0.1 and make the fit again. And you see, obviously, the Q square, the chi square, has changed. So the number is larger. So can we say now that this fit is better or worse than the previous one? No, actually, it's the same. The results obtained for the fitting parameters are exactly the same, but the chi square is different. And why is different? Because I used a different uncertainty, and therefore I'm making this calculation using a constant number here, which now is smaller than before. And if this number is smaller, this ratio becomes larger, and the sum will be larger as well. So no surprises that this number is small. So we cannot compare chi-squares at easy. I mean, you have really to take care on what you do. In the same way, the values of the uncertainty were modified because of the choice of uncertainty that I'm using here. So the uncertainty of the fitting parameters cannot be accepted as we get them from the software we use without thinking carefully how they are obtained. So sometimes it's important, and most commercial software provide uncertainty for the fitting parameters, but they kind of calculate the chi-square for normalized chi-square, for chi-square equal to 1, or for a chi-square normalized to the degrees of freedom. So this, I'm sorry for these technicalities, but I think this probably is a good moment to introduce them in case you don't know. So what do I mean by a normalized chi-square? So let me go back to this value 1 in my uncertainty. So there's 1 again, and I get my fit again. These numbers will not change. Maybe they change in a very, very, very small decimal. And I get my chi-square. So if I take this now, copy, and I replace my uncertainty by the square root of this number, calculate, and my fit, I make a fit again, I get probably the same numbers. Okay, this number seems to have changed slightly. Let me repeat the process. Maybe I did something wrong. One more. Are you still with me?
Yes.
We are with you.
Yes, we are.
Yes.
Okay, so okay, let me repeat the process. Control copy. Okay, calculate and repeat, fit. I'm curious now. Okay. Okay. Sorry about this. For some reason, it's not giving me exactly what I expected. But anyway, no, not happy with this. Not at all. Let me exemplify with a different case. Let me exemplify with this one. There are slightly reasons to explain why I'm not getting what I wanted to tell you from that example. Let me do it with this case. What I'm telling you should not depend on the data that I'm analyzing, okay? It's just that there are side effects that depend on my choices. Okay, so again, so I'm fitting this with uncertainty 1. I get the value for chi-square, and now I'm doing the same thing. I'm using this number, and I'm putting the uncertainty as the square root of this value. Okay, calculate and fit. Okay, this is what I wanted to show you. We get a fit where the chi-square is normalized to 1. There is no surprises there, because if you notice my definition of the chi-square, if I calculate this number with using 1 as uncertainty, I get a number. And if I put the square root of this number, which means q, if I put q here and I recalculate, I will get 1. So this is what I get, a normalized, a chi-square normalized to 1. And then I can say that these are the uncertainties calculated for a normalized chi-square to 1, or chi-square normalized to 1. An alternative is to use the chi-square normalized to the number of degrees of freedom, which means the number of experimental points minus the difference of the degrees of the fitting parameters. In this case, is a rather extreme case, because we have 4 experimental parameters and 3 fitting parameters, which means that our degrees of freedom is 1. So it's basically the same thing. Okay, so now I come back here to the case. Okay, the reason why this might not producing a chi-square of 1 is because I'm using 3 exponential components, and these components affect different areas of my experimental data. So if the uncertainty is larger or smaller, some of these components will be slightly influenced or be more restricted. Therefore, the fit and the fitting parameters slightly change. So we have to be careful with this reasoning. We cannot apply it any time as we wish. Anyway, so I wanted to calculate the weighting factors, so these numbers out of this. So I can go to calculator and reload. Oh, okay, so I have to go back, fit. Okay, and in the calculator, reload. Okay. The calculator receives the parameters from the last fit, and if I clear here, I can easily calculate 1 over, I mean, whatever everything I need. So I can even, I can do that. I can calculate this, or I can select, actually I can select everything. Control copy, and here Control V, but here I cannot use this. Okay, and I can calculate. What's the problem? Inf is 0, exponential, y 0, y 0. What am I missing? Okay. Okay. Still not? Well, that's the risk of playing with things live. Anyway, I will not try to solve the problem. Maybe it's easy to solve it, or maybe it's me doing something that is not. Okay, so I can here in this calculator calculate make any, in principle, any calculation I wish based on the fitting parameters. So this is one thing that this can do for you. In the plotter, which I show, which I use to show this all this data, I'm using this plotter module, which you will find here, plotter. Okay. The plotter can, you can make different types of plots, more rich, because you have better control of most details of the plot, but you can start by importing the last fit you made, and you have everything set for you to play with it. So how does this work in this case? Well, this plot is the combination of 6 data sets, meaning one data set for the experimental points and several data sets for the theoretical curves, which are expanded on this. Each one gets one, text box plus the definitions of the line type, symbols, etc., plus the strings and position or labels, and all that is combined and produces this plot. So that's how I made this large complex set plot, where I combined, in this case, 40 data sets, and each one has its own definitions. Okay, so this is rather crude. For instance, origin, you will have, in origin, probably you have this all these data blocks here, data sets are in tabs or in a workbook, and they are columns, and you select the columns and you produce the plot using the columns that you selected. And for each column, you click on it and you define the symbol, the line type, etc., and the label pretty much in the same way. So it's a matter of how the information is stored and is shown or is hidden, but basically it contains, it will have to contain the same information. So these are the features that are some of the things that you can do with this platform. You can, if you wish, to generate automatically reports. So I just click here on the PDF report, is link below the plot, and I can show you just 1 second. It will make a download. Oh, sorry. Okay, and now it's okay. Okay, so this is the PDF that was generated, which contains the information and the plot. So this you can generate in a kind of automatic way if you wish to have it in a kind of nice way to print. So from the fundamentals of the platform, this is what you have. But what we really need, what we are interested in, is fitting the relaxation profile, okay? And I'm using now, let me show you one example for, let's say, one of the data sets I showed you. This is in your tutorial NMR, so you can try it at the same time as I'm doing it. So I'm recovering this manganese chloride that was data provided by Stellar as a kind of calibration data set. It contains its data for manganese manganese chloride solution with 2 millimolar, and you have the data sets here presented, and the plot is what you see. In this case, is a logarithmic scale and a linear scale. So you have the settings for it. Previously, I showed you that in a kind of different in a different scales. It was logarithmic in the two scales. Let me show you. Sorry. If I put logarithmic, I cannot start in 0. So data plot. So this was is more likely. It looks like the previous plot I showed you this morning when I started. Okay, so this is the difference in what you see by changing the scale. Now, Professor Lanuta will explain you later how you can choose which model to fit to your data. But when we look to data that has a profile like the one you see here, you know that this data it represents the relaxation rate as a function of frequency. The first thing you think is on a relaxation model that at least reflects at least one type of motions with a certain characteristic time. At least there must be one type of motion with a given characteristic time. This characteristic time, in terms of the theory of NMR relaxation, is the same thing as the correlation time. It's a time that I think Professor Nutter yesterday explained you well. It's a time that just characterizes how much memory the system has from its past. So how much from, let's imagine the rotations of the molecule. So I have a molecule, which is my stick here, and how much can I tell if I look at the molecule at one moment and it is at this position, how much can I tell from where it was sometime before? So it was moving, it was rotating from this position to that position, and how much memory does the system has? If I look at the system at the molecule at this position, can I anticipate from where the molecule comes from, and how far back can I go and still be able to be sure that the molecule was coming from that position? So it's the correlation is also related with the memories the system has from itself. And when we think on this characteristic time and on this correlation, we end up, for reasons that Professor Danuta explained yesterday, and probably will, or even in the afternoon, there was some presentation. It turns out that you end up by thinking on expressions like the one I'm writing now, which is a sum of two Lorentzian curves. Are you there?
We are there.
Yes, we are.
Yes, we are.
Okay. So this is commonly known, or at least I'm used to call it BPP, Bloomberger, Purcell, and Pound, 3 Nobel Prize winners that developed this or came out with this first expression for the contribution to the relaxation rate coming from some motion which has a certain characteristic time tau. And the first thing that you must know when you try to fit data, you must have some idea how the theoretical curve looks like in a given presentation. So you have to know how this function looks like when you plot it, okay? And the way you plot it will affect your perspective from what your curve is, what contribution, how it looks like, how it behaves. So if I have a linear scale, okay, 1, 2, 3, etc., and this is omega, and if I have 1 over T1 on the y, also in a linear scale, it's likely that this curve goes something like this, okay? And somewhere here in this position where there is this inflection, when it starts going from one curvature to the other, is about the point where omega tau is basically 1, okay? And this is how it looks like in a linear scale. If you look at this same function in a log scale, so this is log of omega, and this is log of 1 over T1, the perspective is different. And what you see is something that is constant, and then it goes like that. Here is flat, so it's a horizontal line, and here the line goes with a slope which is -2. So this is omega -2 at the end. Okay, so this is the typical thing that you see. Now, if this is the type of image that you get, or the representation of this 1 over T1 represented by the sum of these two Lorentzian curves, when you look at the data here on the screen, I can, and let me try, okay, I don't have the data here. Okay, I have to draw it by hand. So I don't know if I can annotate. Does anyone know if in Zoom I can annotate on my screen myself?
My knowledge, not.
No, so I cannot. Okay, let me see. Ah, yeah. Okay.
You can? Okay. So,
Yeah, I can. Okay, so here is one.
then
Here's one. I could imagine.
I will use it. Perfect.
I'm using, you see, I can imagine 3 curves going like that. And, well, why don't we try? Okay, now I have to close this. Ah, not close. Okay. Ah, well, it's nice, but I should have removed it. Annotate. Sorry about this. Delete, clear all, go out. Okay, so let's do that. Let's imagine that these are there are three components, such as these ones that I'm using here, these 2 BPP, 3 of them. Okay, so how do I write them? Okay, I can write them in the same way I'm using here. So I can start by saying A times, open parentheses, and then he is 1 divided by open parentheses, and so on and so forth. And I can write pretty much in the same way as you see it here written in using this usual mathematic, this formalism. But Fitteia has already some of these relaxation models built in. And we can, you can look at them going to the page, the main page. So let's look here. You have one particular entry in this menu is this NMR Relaxometry. If you go there, you see a place where I combined, or let's say we in the community combined some models already for you. So we call them, or we put them in this under this name, NMR Fitteia. I'm afraid it has not evolved much in the past, but well, it has its uses, like the one I'm giving it now, I'm using now. So relaxation models. What we have? We have basic rotations, translational diffusion, collective motions, paramagnetic relaxation, polymer, others. Let's look at the basics. The basics are the mono-exponential, bi-exponential, etc. So things that we used already. I showed already some examples. Let's talk of rotations. Okay, BPP. Let's check. This BPP contains, in this particular case, some additional information. In this particular case, it introduces this and explains lots of things and gives you back some codes, some examples. So if we want to use this previously compiled model in our fitting, it's enough that we copy this and we go to, where was it? Here. And I put it here. And now I have to say that this contribution has one A rod and one tau. And I can try it. I can make a compile. Okay. And I can try, okay. I should have made it, sorry, normal again, not, okay, and fit. I'm afraid is not so impressive. And actually, I doubt that this is the best fit. Obviously, it could not be. So I'm getting a fit, or the system returns some values, but definitely is not a good fit, is it? Obviously, the curve goes away from the point. There is no way this output corresponds to the best fit possible. So okay, so I'm trying to fit and I'm getting some result, but it's not the best. So how can I trust the system? Okay, the only way to trust the system is really to trust your eyes. So actually, your eyes will tell you if it's acceptable what you get or not. So as long as the curve does not go over your points in any acceptable manner, you cannot accept what the system gives. But why is the system giving you this, which is so obviously wrong? Because probably you are telling the system to try to minimize the chi-square, starting with values for your fitting parameters, which are quite far away from the values that are actually acceptable for this system. And so that doesn't help you much, because it's like telling you or asking you to give the right parameters before you getting the right parameters. So it's a closed loop. I cannot answer before doing the fit, but to do the fit, I need a kind of the right answer. So, well, if you don't have the right answer, you have to at least try to do as good as possible. So for this purpose, in this particular case, sometimes it's provided the values that you should consider as acceptable. For instance, A rod is this pre-parameter, and actually most users consider this as a free fitting parameter. But actually, if you go to the introduction, you'd see that this prefactor, so this ABPP, is actually something that depends on the dipolar coupling constant. So it basically depends on a kind of average of distance between your nuclear spins, and obviously the strength of the dipolar interaction that depends on the gyromagnetic ratio of the nucleus that you are looking at. And this number, although it is a free parameter, at the same time is something that is very much related with the molecule, the structure of the molecule, and overall how the molecules are organized. So it's a free, but you don't have, you are not, it's not free in the sense that you can have a choice on the value that you can use. And so usually is a number which is small, and probably, let's say, here is a rather broad range. You see 0 from 0 to 10 to minus 12. So 10 to minus 9 is a possible number. 10 to minus 8 is also a possible number. So here, in this case, there is a rather broad range of values that are possible. Anyway, you have to try. So let's see here if it works. If I try to find a minimum, which is around 8, and 8 for A rod, power 8, which was okay, because here it is written 10 to 9, here, 10 to 9, and here is 10 to minus 12. So here I'm choosing 10 to minus 9. And let me see if how the theoretical curve looks like for these values. And for that, I'd use plot. I make a simulation. Okay, so it's too low. It's a number here. So let me make 9. Plot. Okay. This one seems to be able to fit already this. Maybe this is a little smaller, so 8. Ah, too much. So maybe I put here 8. Plot. Okay, so you see, I'm probably will be able to fit my data by trial and error by doing that. And if this black curve will be able to fit this data, maybe with a second one, I will be able to fit that part. And with 2, I will be able to fit them all. Okay, let me try now a fit. And, well, I couldn't expect much more than this, because after all, I'm using one curve, one theoretical curve that has this particular shape, and definitely our data does not at all as the shape of the curve I'm using. So probably I should use not 1, but probably 2. Okay, I'm using this backslash to put 2 of them. The frequency is the same, but probably I should use here 2. And of course, I have to use the same, declare the variables here and compile. Okay, I'm using these numbers for the previous curve. Why not to use the same as starting values for the second BPP? Okay, is a guess, probably as good as any other, but I will know at least where the second curve will go. Actually, if I plot both of them, they will be superimposed, of course. So I will not do this obvious thing. Okay. They all look black because I didn't care about changing the line types and the colors. Okay, but now they will look like this. Well, you have to agree that is better than before. Sorry. But it's still not okay because something is missing here. So probably these last sum of should be, maybe a constant. Okay, why not put a constant here? B. Okay, compile. I can even guess what B might be. Eventually, B should be around 10. Let's see. If I plot. Yeah, maybe. But then the blue curve and the red curve have to be slightly smaller. So let's make a fit. Almost perfect. I think you will agree, right? It's a very good fit. Well, I'm guessing that I'm telling you that it's very good fit because it looks good. Not necessarily because this number is the smallest one. You remember we have been there, right? I told you that this number, it's a good indication, provided that I'm looking alone to this data set and to this model, and the smaller the number is, then I can rely that this is a good fit. But I cannot use this number to compare with any other fit made by any other person or any other model. Okay, I have to be able to compare using the same uncertainty. Okay, I'm sorry. Okay. Okay, but I'm fitting this data. I'm getting a good fit. I think Danuta is, Professor Danuta, you are complaining because I don't want to anticipate what you will be telling later, but well, anyway, I'm using this BPP and I'm fitting the data. Should I be happy with this or not? And the question is now is, I'm getting these numbers, A-rot and A-rot2 and tau2. What do these numbers mean? What correlation can I establish between these numbers and the numbers and the characteristics and the physical constants of my system? I have to remember this is water with a little bit of manganese chloride. And water, a water molecule is an oxygen with two hydrogens. How can water has rotations which have such difference in characteristic times? So how can water be rotating with two different characteristic times? So although I'm fitting the data well, it looks nice, the curve goes almost through all points, but the numbers have no meaning because I cannot understand how water can rotate with such a, 1 order of magnitude of, and even this parameter, which depends on the distance between water molecules, how can it be that there are protons at different distances and it's water? And it's a little bit of manganese chloride, which has no hydrogen, so I cannot rely on that. So this model produces a nice fit, but it's not give anything. Yeah, so we have to be a little bit more specific about the choice of models that we use. And in this case, we have to use a model that takes into account the presence of these paramagnetic centers. I will not go into detail. I will leave that for later talks. Because the presence of the manganese chloride, as I told you before, introduces this this relaxation enhancement due to their presence in the system, and this relaxation enhancement has its own model to explain the data. These models are also available here in the NMR Wikipedia, and it's these equations which are actually there. So this is one equation. There is a references for both of them. One is from Professor Danuta. And actually here is exactly the example I'm giving you, okay? So you can find, you can have it in the, well, when you fit the example that you have available already for you, it fits the data. But now, if you compare now these fitting contributions, the blue and the red, and if you look carefully, there is some green here at the bottom. These contributions are different from the previous one when I was using this BPP. And one of them is this inner sphere, and the other one is the outer sphere, which has which are the two contributions that we can associate with this enhancement in relaxation caused by the presence of water. Actually, I can tell you that the inner space is related with the water that somehow binds together or stays correlated with the manganese chloride during a certain correlation time. That's called inner sphere. And the outer sphere is represented by all the other molecules that are diffusing around the manganese chloride without actually binding or staying together, staying around the manganese chloride for a while. So this is called outer sphere. So this is one example on how you can use Fitteia and choose the models and the combination of models to fit the data as you wish. You can do that in a one-by-one cases, or you can use this master module to help you do things in a different way. Please note, I'm on basic here right now, and I choose this master to MZ profile and I recovered. So I have here the data for this master MBPP. And what is shown is not only one data set, but several data sets presenting the same graph. These data sets are here in the same text block, but they are now separated in what I call blocks, data blocks. So one data block for 298, another data block, these actually are temperatures. So this is for 388 and so on and so forth. So we have 4 data sets corresponding to 4 different temperatures. And if I look now in the master and I do the same thing, recover, sorry, not this one, this one. I get, I didn't show the complete picture. I should have come down. This is lots of data blocks. Sorry, I choose again the wrong one. This one is what I wanted. I apologize for this hesitation. So 4 data sets, 4 data blocks, and now I can use this model to fit the data one by one. I select the ones I want to fit, and I fit, and it will perform the fits, the independent fits of each data set with using a model with the same expression, and it will give different parameters for each one of them. We see that they are different because you see the contribution change. So the contributions are different in each one of the data sets, and the output parameters for each one of them are here in this table. So each data set has its own set of fitting parameters. Some of them are constant. You some of these parameters are constants for this fit. Others are being freed, and we can get the best ones to get your feed. Okay, so this is what you have for these 3 data sets. I can show you now a little bit more realistic case. Let me check. This is my area, my account. So in my account, as you can see, there are lots and lots of systems, okay? Lots and lots of systems. Let me look at the cheese cases, okay? Master. Okay. This is a collection of data from Moreno, from Stella, and was, let's say, part of the work that was done in this network devoted to dairy products. And you see here we have 19 data sets obtained from different cheeses. They are very similar, but if we look carefully in one of them, we see that the data is similar to what we have seen, but there is some oscillations here. Professor Danuta will explain you why there is this kind of enhancement in relaxation in some restricted areas of the dispersion profile. This is usually associated with cross relaxation. So the professor will explain you that. But this has a specific type of model that can be used to explain this enhancement due to this cross relaxation. I will not go into the detail here. You can have that as well as here in the NMR-DPD, where you have the same function written here. Some other simpler expressions. Actually, you can check what this function is. It's a function that produces this type of profile, and you have the expression here. But you can find it also on the references to this paper, in particular one of Professor Danuta's papers. So where was I? Here, no, here, no, here. Where was I? Oh, I missed. No. Yeah, here. Okay, so let's fit them all. So I pressed fit, and is applying the same model to fit all the data sets, one by one. Of course, you can use this system not to fit one by one, but to fit all the systems with the same model and with the same fitting parameters. Of course, in this particular case, that doesn't make sense because the systems are completely uncorrelated to each other. The only common characteristic is data obtained from a cheese, but the cheeses were different, with different type of preparation, different type of milk, different origins. So they are not correlated, so they could not be fitted with exactly the same equation and the same fitting parameters. So it makes no sense to think on a global fit with the same set of fitting parameters. Instead, we are fitting them individually. So it takes a little longer, but you see the fit is not so simple as before. Let me show you one example here. I don't know, each one of them is good. Okay, that's the first one. So what do we have? We have that this profile has curves that look like this BPP, as I showed you before, plus this enhancement due to this cross relaxation. You might wonder what evidence is there to justify this red curve. And actually, this red curve that looks funny on this scale, actually, it only looks like that because I'm plotting the data to a very high frequency. If I put this here to, let's say, 1E8 and just plot, just to show, well, I should have chosen just one to make it faster. Anyway, what we will see is that because we are just now restricting the representation to 100 megahertz, the red curve will not show this decrease here. So it will be as if we were using just a straight line, just a constant that was added to the relaxation model. Okay, because we were ignoring what happens at higher frequencies. The fact that this is a constant and is not a curve that will go down here, we cannot decide unless we suspect what the relaxation rate will be at higher frequencies. So if we can anticipate that the point corresponding to this cheese, the relaxation rate measured at, let's say, 100 megahertz, if we suspect the point would be here, somewhere in this vicinity of this, of my mouse, then the red curve would have to produce this contribution that would bring the relaxation curve down to this point. And we don't know because we don't have experimental data in the high frequency. Okay, I think we are getting to the end, and I think it's time to give you the opportunity to ask questions and make comments. I'm not sure if those of you that register in Fitteia were able to reproduce some of these feeds. I hope you are able to do it. If you face some difficulties, please let me know. Hello.
We are alive. At least some of us.
That's not bad. That's not bad. That's not bad. That's not bad. Roberto, I should have mentioned you because you are at the origin of these feeds and also at this analysis. I apologize. Roberto Aneda
Hey, it's okay. Thank you.
He's here and I thank him very much for these data sets and for the opportunity to discuss all this with him. So for those of you that will eventually face some NMR profiles in the future, my only advice is that you choose your software, think on the pitfalls that you will face ahead and try to prepare yourselves. And one way to prepare yourselves for that is to look at the equations and how and simulate the curves. I mean, basically draw the theoretical curves for some common or known or let's say relevant parameters in order to anticipate the combination of contributions that you will need to fit your data. And I rest my case.
Can I make a comment?
Please, Roberto.
Yeah. Okay. First of all, thank you. Your presentation was very clear, and I bet also people that is not involved in NMR relaxometry would understand that the potential of this application and of the technique itself. So my comment is, starting from a system that we don't know at molecular level, let's say even a very simple system like water with manganese, which is like paramagnetic element, of course, and we need to know something about how the system behave on an NMR relaxometry point of view. So we know that we have some elements that are paramagnetic, and water is diffusing, and it's a liquid system, and so on. This is a pretty simple system, right? So we know almost everything at molecular level, and we can speculate how it would behave from the NMR relaxometry. But let's say this is a very simple system, which is unusual to find in a food chemistry or food science. When we move to more complex system, where do we start? I mean, we should start from the very simple considerations first, and then move to more complex interpretation of systems, right? So what is the steps that you would follow to explain how the system, how a complex system behave?
Okay. Thank you, Roberto, for the opportunity to address this point. Yes, I cannot give you an answer. Well, I will try that my answer will be a guideline to all situations, but actually it will not answer any one of them in particular. Because it is more like a guideline than anything else. The first thing is that if you really, let's say, if you show me some relaxation profile without telling me anything about it, I will, let's say, sorry, let me try to, sorry for this hesitation. I just want to, where was this? Okay. You remember this, you are able to see my plot, right?
Yes, we can see.
Okay. Right now is a mess, right? Right now is a mess. Is a mess because, you know, every data set is superimposed and I cannot easily distinguish them. So if you show me any data set that you might come up with, you show me to me. Well, based on the all the data accumulated, available out there, I'm pretty much sure that the relaxation profile will be here. And it will show some features. Some features are, let's say, better identified than others. For instance, it's flat in the low frequency region. And what type of slope do you have here? Is it a slope of this type, that like I'm drawing here with my mouse? Or if it's a slope like this type, like I'm drawing like that? And that in this, if I have this type of slopes looking in a log scale, this is something that you find in a system like this. This system was a pectin gel, so it's sugar-based things. They are sugar molecules, sucrose, monosaccharose, etc. Glucose, all these sugar combinations, and there is water in the system. And the profile is very steep. So this has some meaning. It means that from all relaxation models available you are in a frequency region where you are probing the high frequency regime in all the models, pretty much. And this has some meaning. It's a very slow diffusing process. The rotations are slow. Everything is it's a very viscous system, basically. Okay. Then if you look at the data and you see, well, it's flat and the relaxation profile is not very high, then it's likely to be a very fluid system, not very viscous system. And then you have this other set of data which has this slope, which is roughly 1/2. If you measure this slope, is roughly 1/2. And this is typically things that you find when you have small molecules confined. So if you show me cheese, or if you show me any other system where you have small molecules confined in a more solid matrix, porous matrix, or mesh of some sort. It might be water, or it might be another small molecule, a sugar molecule, a monosaccharose or disaccharose, moving in a restricted environment. So it's likely that you will produce a distribution profile with this type of slope. And of course, then there are more elaborated analyses that will show you eventually if you are facing something that comes from a strong interaction between the molecules and the surfaces of the encapsulating walls, of the walls that encapsulate this more mobile system. So you will be, you can build up or start a list of hypotheses based on the relationship that you have looking at your data and data accumulating from other systems. One particular evidence is if there is paramagnetic relaxation enhancement. In some cases, you can see it in an obvious way because there is a strong enhancement. Other times, like the manganese chlorine, is not so evident, except that the whole dispersion profile goes up. So the bottom line is that you will be able to ask some questions, and trying to answer those questions will make you understand what is the composition of your system. Is it very viscous? Does it flow? Does it not flow? Is it heterogeneous? Is porous? Things like this will help you to restrict and to look at your data in a different way and keep asking questions and trying to see if the alternatives that you will find, the relaxation models that you have available, are consistent with the hypotheses that you make. So you will not be able to get a definitive answer, but you can measure the quality of your analysis by the self-consistence between the hypotheses that you make and all the information that you can get from the system. Sorry, I cannot give you any better answer.
Thank you. I think it's clear. And if I can have other comments, if there are no more comments from other people.
Yeah, please, as long as you wish.
So the question is, let's say you realize you have several factors that affect your NMRD. Yes. Okay, and you just keep adding factors to your model, like several BPPs and paramagnetic ions that would interfere. Let's say there is bulk water dispersed in your matrix and so on and so forth. And you end up having a very long list of parameters. Yes. How do you know you are not overfitting your experimental data?
It's very easy to get to get in a situation that you are overfitting your data, and especially because, let's say, let's say Paramagnetic relaxation enhancement is a model that depends on several parameters. Most of them you don't know for your specific system. Then what you can do is use values for those parameters that you don't have access in your system, to use those that have been published for similar systems. So we should try to avoid using the parameters we get from the specific analysis that we are making, ignoring what the values of these same parameters have been or were obtained for systems that are similar. So we have to compare our parameters with others. And when we don't have values for our case, we have to use the numbers from other systems. And the best, I mean, the answer, I mean, my answer to that problem that I faced already in the past is that all my analysis becomes dependent on that hypothesis. So I analyze my data, assuming that I'm using parameters that I really don't have access for my specific system, but I'm based my analysis on the values for similar systems. And similar here means I find some reason to assume that I can use those values because the molecules are as elongated as mine, or as many spins as mine, or the structure is this or that, or I expect my system to show evidences of this collective motion as the other. So I have to justify my similarity and to justify my choice of these values, of these parameters that I cannot obtain directly, but I'm supporting my analysis on those values that were, let's say, hopefully better determined for those systems. In paramagnetic relaxation enhancement, that happens a lot because there are several parameters, electronic relaxation times and all that we don't have access for our specific system. Over-parameterization is very easy to get into that problem, and one way to avoid it is again to try to do your best to correlate your fitting parameters with actually physical parameters from your system, like distances, viscosity, diffusion, temperature, whatever physical constants you can get from your system, the best you can rely on your fitting analysis.
Thank you, and this consideration also suggests another question, if I can, of course. How do you think complementary measurements are sometimes needed to interpret your NMR data? I mean, are they always needed? So, for instance, making measurements of density, of protein content, fat content, and so on.
Sure. I mean, for instance, if you play with systems where you can use the word fat, so fat is basically molecules that don't like water. How to say that? Hydrophobic molecules with hydrophobic groups. So molecules that don't like having water in the vicinity. So they are apolar chemical groups in their composition. Knowing that is a good hint, and being able to say something about the percentage of such fat content with respect with water or whatever non-fat content is important. at several levels. First, to know what type of motions can come from the more mobile with respect with the more restricted. This is one possibility. The other is that you might have a situation because you have fat in one area and water in another. Eventually there will be there will be not enough spin diffusion, so there will be not an homogeneous relaxation, and you might have actually two relaxation pools. So you have systems in the fat area that will relax in one time, and systems in spins on the more on the other environment relaxing with a different time. So you can, in that case, you can separate, and you have a support to really analyze your data on the basis of two different pools of spins relaxing with different relaxation times. So being able to support your assumption is crucial, is essential. Okay, you have the density, you have the fat content. If you have X-ray or X-ray data, it's important because that reveals some level, some structure, some information about the structure of your system. So all these complementary analyses are essential to interpret your data. Okay.
Thank you.
I think that's why you demonstrated really fantastic tool.
Okay, thank you. I thank you very much for listening. You can contact me at any time in case you need some additional information or help. Okay.
I mean, it's like
my message to take back home is that don't be overconfident that you are able to answer everything, but also do not look at this data as something that will tell you nothing, because honestly, it will tell you a lot, but you really have to ask the right questions and to build the answers supported in the comproved or proved hypotheses. Okay.
And one must have a kind of, let's say, well, one always must have a kind of knowledge, let's say, put it in this way. But here, quite often, okay, if we gain experience, we can already guess what we can expect for some systems. And they probably will also gain this expertise in time. Yeah. However, there are some basic things which one must know. Like one must be aware that there is a different relaxation scenario in paramagnetic systems than in diamagnetic ones, and so on. Because the most unfortunate thing is to make mistakes at this level.
Yes. Yes.
Because later one can really discuss, whether I see polymer motion, chain motion, or dynamics on a surface of larger molecules or something like that. But this is a different level of discussion, which might raise controversy. It might happen that you do not get straightforward and clear answers. A lot of things can happen here. Yes. But the relaxation scenario must be clear.
Yes. Definitely. I mean, I choose a bunch of data to show you, but for instance, I did not go into these high viscous systems like, glycerol and all these almost gel-like systems, or even polymers or nanocomposites on these systems. So things can be even more complicated than the ones I'm speaking, and the type of complexity can be completely different from the fact that we have a system composed of many components. It can be a simple system and still be very difficult to understand and analyze. So the type of complexity is different. So you have to we have to build up our database of knowledge in a given niche of or area of activity. If you are doing dairy products, the best is to start building this database of data, of knowledge, of analysis, of parameters, of values that will help to support the analysis, because every time we find a system that does not behave exactly as the previous one, it will provide new information that will help you not only to understand the future data sets, but also to reinterpret and to reanalyze the previous ones, because you were enlightened, because you have more information now to look at the data from the past and look, oh, I was not aware at that time that this is like this, therefore my knowledge improved because I know more now and I have all the data before to help me to support this new analysis. So yeah, so we have to build up this database of knowledge.
Thank you, really. And you know now that even if you, how to say, feel that you need a lot of time to gain experience with this tool which Pedro presented, the tool is at your disposal, yeah? So there's something you should play with and start to and try to understand.
Okay. I must tell one word about this. I talked about this thing that I showed you, this Fitteia thing, okay? It's just a tool and is no better or worse than any other tool that you might find or wish or develop yourself. That's his first point. It does nothing more than nothing less than any other fitting program. What it does right now, that incorporates a kind of tricks, techniques, ways, strategies to analyze data because of the diversity of systems that I faced in the past. That's all. So most of these things you will probably never need to use. Some of the things might be some of you might find useful, some others not. So yeah, it's a tool available for you to use, but you can do yourself in MATLAB. I saw someone on the audience doing the things in MATLAB. Yeah, it's perfectly all right. You can do everything that I showed here in the MATLAB in the same way, or Origin for that matter. It's not different. It's not different. It's just a different way of organizing the things. What I try to show is that, well, in my perspective, there are some strategies sometimes that help to get faster to your goal, which is to, read something from your data.
Yeah, but nothing helps if you do not understand the meaning of those parameters, the concept of the numbers.
Yes, definitely. My starting point for all of you newcomers is that if you have a function, draw the function. Find a program that is able to draw the function, make a plot to see how the function behaves when you change one parameter, when you change the other, where the curve goes, how it changes, because it will help you. It will guide your mind on the process of fitting the data. That's my bottom crucial point.
So thanks a lot.
Thank you.
And I think we should make a break now, a lunch break. So we see each other at 2 p.m.
Okay, I stop recording now.
Mm-hmm.